So in a unit that is called Newton's third law, where we're studying multi-body problems, do you recognize that there's three objects here? So we had to augment our rules a little bit to accommodate the fact that there's multiple objects. One of the accommodations is that every object with mass is represented by its own dot for its own free body diagram. The next thing I suggested that you do is choose a common direction for the direction of your acceleration of your system. It was asked by somebody in sixth period, well, what direction is the system moving? I don't know. It doesn't have to be moving. An object can be accelerating and not have a velocity for an instant. Right? I throw a ball in the air, it will stop before it comes back down. There will be an instantaneous moment when it has no velocity. I'm saying this to you guys because what do you mean when you say motion? Is it moving? I assume moving means it has a velocity. But this is a moment in time. I don't know if it's moving or not. And then somebody else asks, well, is it accelerating? Well, if you don't know, what must you do? There's a rule for it. You know? Second law. If you don't know if it's stopped, if you don't know if the net force is zero, you must assume it is a second law problem unless proven that is a first law problem. These are the rules. I gave you a set of rules. Just follow them. I look at the first car and start asking your questions. Is there a gravitational force acting on the first car? Yeah, I'm not even going to draw it, though. Because I also know there's a normal force in the ground. They're going to sum to be zero. It's not accelerating upwards or downwards. And since there's no friction, am I going to use that normal force for anything? No, I'm going to ignore it for now. But I do know that there's a 30 Newton force acting on the first car. I am forced to use it. It was given to me. Is there anything in contact with this car? String. Strings pull in the direction of the string. I don't have a choice in this. And so I don't have to think deeply on it. The string has to pull that way because that's the direction of the string off the first car. That's it. Let's go to the next car. Because there's no friction, I don't have to ask about resistive forces. Yes, there's weight on the second car. Yes, there's normal force in the second car. Do I care about that at this time? No. I could draw it, but I have to draw an arrow 20 or 4 times bigger than whatever weight arrow I would have drawn here. Not sure that's super necessary. Is there a string attached to the car? Yes, there is. I don't get choices here. That's 2 strings attached to this car. I got a string this way and a string this way. I'm pretty sure they're not the same size because I'm pretty sure this car is going to be accelerated to the right. So I'm going to purposely draw them of different sizes. But I know more than that. Although they're both a tension, I'm starting to get a lot of T's here, right? But I know things. Newton's third law says for every force there's an equal and opposite reactive force. I think that's the tension in the string. I think this tension and this tension are the same. That was the additional piece of information given to you yesterday. And I think that there's a tension here, and I think these 2 tensions are the same. All right, so tell me what we've done so far that's been outside the scope of what you've had in this class. All right, so I move on to question 2, which was to find a Newton's law relationship. All right, this is it. All right, I'm going to apply that, add up all the forces, set it equal to MA. Each one of these has just a couple. I'm thinking 30 minus T1 equals 5A. How are we doing with that? Not terrible, right? Anything outside the boundaries of what we've talked about. All right, T1 minus T2 equals MA. Different M. This acts on the middle car. Have to use its mass. Last one, this one's tough. T2 equals MA. Now we pause. Ask ourselves, are all these the same? Does this object move in such a way that the acceleration of one is the same for all? If the first car moved 10 centimeters, would they all move 10 centimeters? Seems not unreasonable. If so, then I have 3 equations and 3 unknowns, right? T1 is an unknown, T2 is an unknown, and A is an unknown. You're asked to find all of them using any method you want. Row echelon elimination, Kramer's rules, or how about just substitution? You know some things, maybe not all of those things, but you know some of those things. Of course, you could do what I suggested. Just add them up. If you do this right, you should find that internal forces cancel out. So if I just add these up, I see a negative T2 and a positive T2. If I add those together, they're going to add up to be 0. And a T1 and a negative T1, if I add those together, they will add up to be 0, suggesting the only thing that is left when I add up all 3 of those things on the left side is 30. If I do the same thing on the right side, I pause here on purpose because one of the things I noted yesterday was that if you do this right, you will get an overview of the system. And if I didn't make that clear in this class, then let's make it clear. The internal forces all canceled out, and I'm left with just the external force here. And it's saying that the external force will be equal to the inertia of the system times the acceleration of the system. This is an expression of Newton's second law over the system. If done right, you will see this in any problem that has multiple objects with the same acceleration. It's a way to know that your arithmetic has been done correctly. Of course, this also tells us that our acceleration is 6/7 meters per second squared. I believe that's 0.86 meters per second squared. Now, if you want to go find T1 or T2, you had to get the acceleration to do this. And I'd probably start here with T2 equals 10A. Not the hard questions yet, right? I'd argue this is the guys like having the numbers better. So I apply an external force on both of these systems. In which case would the normal force between the boxes be greatest? Case A or case B? You do understand there's a normal force between the boxes, right? Probably constitutes Newton's third law force too. One box touches the other box touches back. Now you could solve for the answer, sure. I mean, just say this is 30 newtons again and try. But I would prefer you consider, is there a reasonable argument that could tell you which of these two cases would generate the larger normal force? I think there is. But again, if you don't like that, just give your force a number and find out which normal force is greater. Pick one of those and be able to provide me with an answer, whether it's case A or case B. A divergent thinker can still come to rational conclusions. So when applying or trying to justify yourself, You could have said, all right, I'm just going to make 30 newtons for both of them. Why? Because it's a nice round number and the total mass here is 15. If I do that, the acceleration is 2. And if they both accelerate at 2 meters per second squared, this box is going to need 20 newtons of force, and this box is going to need 10 newtons of force. Right? I could do math on it, and that would be a fine justification. But if you're going to try and justify it using some kind of prose, which you may have to do, then in your justification, pick a law. Have that on your side. Because the law is going to work. You want to pick the right one. That generally does better. And in this case, it's not a Newton's third law that would help. It's just force equals ma. I fear adding, but we need to add. Let's take those two boxes, bring them over here. All right, 10 kilogram box, 5 kilogram box, hung by a light, non-extensible thread over a massless pulley. Fake physics stuff all the time. But this is what we have. This is called an Atwood machine. This is a standard Atwood machine. It's not a modified. It's used to study inertia. But it's also actually used in places. There are plenty of situations in which you would use something like this, having a counterbalancing weight to assist a motor and perhaps lifting something. That's what this could do. So maybe you have an elevator, and so you use a counterbalancing weight to lift the elevator. This is common. I'd like you to find the acceleration of this system. I think that's not an unreasonable question. And maybe the tension in the cable, that would be a good one too. But more importantly, I want you to draw a free body diagram that accurately represents this. I think that's more important. A free body diagram that accurately represents this. Bless you. Now, we have more than enough time to see this all the way through. So I want you to. So again, I think there's 4 things you have to do here. Think a free body diagram. I do not believe you'll guess at an answer, but I think a free body diagram. I think an appropriate net force equation for the blue box and the green box. I think you can probably use those equations to figure out the acceleration and then probably go back and figure out a value for the tension. Give it a try. Again, these are not terrible, right? Are there any questions about this? I do want to kind of back this up just a little bit and just make a quick couple of statements. So let me get back. The tensions have to be equal because the pulley is massless. That's not going to be for the whole year, but it's going to be for this semester. It is the tension in the cable that is tempering the motion here. The 50 Newton mass is being pulled upwards by this tension, but the fact that there's 2 masses, that's creating the tension. What's important for you guys to recognize and to be able to implement here is that you're just generating the same sets of relationships we did before. But to make it consistent, there are just a few additional steps that help out. One of them is this step, making sure you choose a direction for the acceleration. That's the same for both. The next thing that helps out, and this is just, a problem-solving thing, is to make sure that you ask yourself, will the accelerations be the same? These are just little things you have to do. They're additions to our set of things, but that's because there's multiple objects. So in seeing whether these multiple objects are operating dependently, and we ask these kinds of questions. The tension here isn't really a Newton's third law force. again, the tension acts on the pulley and the pulley acts on the mass. But solving the problem still just recalls taking our system of equations and figuring out that we can cancel out the internal force, leaving us with a net force equation for the system. This is the net force equation for the system. The system's full mass is 15. There are two independent forces attempting to accelerate this system. It would be no different than if the blocks were sitting on a table and I pulled with 100 newtons in one direction and 50 newtons in the other direction. The result would be this acceleration. Now, when we get the acceleration to be 3.3 meters per second squared, and you go back and find the tension, I do want to point something important out. This bar right here, the whole system is suspended from the ceiling. The pulley has a net force of 0. Do you think, if the pulley is massless, do you think the upward force on the pulley will be greater than 150 newtons, less than 150 newtons, or the same as 150 newtons? And you don't have to guess. You just found the tension, right? If we look at the net force on the pulley, there's an upward force from the bracket and 2 downward forces from tension. You can find out the answer. Now, we've hung a 50 Newton mass and a 100 Newton mass from the pulley. That's why I'm using 150 as my threshold value. And I'm asking, if the upward force is greater than that, less than that, or equal to that? Don't be surprised. Look it up. Find out the answer. Solve for the tension right now, and somebody tell me what the upward force on the pulley is. You have time. Well, 60 seconds. All right, so the tension, 66.7 newtons. The upward force in the bracket, therefore, which is 2 times the tension, is 133.4 newtons. Now, that's clearly less, right? Does that make sense? Why? I want you to hear this before you guys run away. Net force on the system has to be unbalanced because the net mass of the system is accelerating downwards. I don't have to pull up with 150. If I'm pulling up with 150, then the weights won't be accelerating downwards. But a big mass is accelerating downwards, and less mass is accelerating upwards. So the net mass of the system is accelerating downwards. We need an unbalanced force for that, which is why the system does not pull up with the weight of the system. It pulls up with something less. This is a more complex conversation.